So today we're going to be talking about length contraction. We will be branching off what we did previously with time dilation. So we need to start off by defining a ruler. Rulers are used to measure a distance. So to do that we need some form of rigid rod of a known length. But how do we measure that length? Well, similar to last time where we used light to measure a tick between a known length, we're using a light tick to measure the length. So this rod here is a stationary rod that we are measuring the length of using the speed of light and the time it takes between the ticks. So to calculate the length of the rod, we do delta x equals a half delta t, which was the round trip speed, times c, the speed of light. Now if this ruler gets put in motion, the diagram begins to look a lot more complex. So to start off with, it looks like we've got a similar setup to before, where we've got the light and a distance, delta x prime. This distance isn't equal to delta x, because it will have been changed due to the relativistic physics. When a photon of light gets emitted, it has to travel a distance d1, which is comprised of two components, delta x prime and v delta t1 prime. This extra term is brought out of the fact that the mirror that the photon hits would have moved further away in accordance to the speed that this train is going. It would have moved further away than when the photon was initially emitted, so it'd be a little bit further away. So this is an additive section. Now we're measuring a round trip speed. So for d2, which is for the return journey, the photon of light bounces back, and it bounces back for a distance of delta x prime minus v delta t2 prime. The reason why it's minus here is that the light would have caught up to the mirror slightly by the time the photon bounces back. So this distance will be smaller than this distance. Now, there's a lot of maths here, so no need to worry. So to begin with, we're doing the outwards journey with d1. So d1 equals delta x prime plus v delta t1 prime. This is also equal to c delta t1 prime. This will just be the speed of light and the time for the outwards journey. We can rearrange this to get delta t1 prime. Now for the return journey, we have the same, but be aware of this minus. Apart from that, we've got the same equation. We've rearranged it down here. Take note that in the rearrangement, because of that minus above, we've got c plus v at the bottom here, and not c minus v like we did for delta t1 prime. Now to get the round trip speed, we are adding both of these together. So we're doing delta t prime equals both of these added together, which is 2c delta tx prime over c squared minus v squared. Now there's some things that need to be taken into account before going to the next steps. So previously we did delta t prime equals 1 over the square root of 1 minus v squared over c squared times delta t. From now on, we are going to be using gamma to express this. We'll be using gamma because it will be a lot easier when cancelling out factors of this. Before, in the first slide, we stated that defining the distance was delta x equals a half c delta t. We can rearrange this to get delta t equals 2 over c delta x. Moving on, I've just restated the values using gamma over here. And I've just rearranged that last bit of the equation by dividing by c squared, and this has given me 1 over 1 minus v squared over c squared. This is gamma squared. You'll start to see why I've swapped out gamma, because that's a lot easier to notice. So inputting what we've got above, we've got 2 over c gamma delta x equals 2 over c gamma squared delta x prime. We can rearrange this to get delta x equals gamma delta x prime. What I'm going to do here is I'm going to rearrange it one final time. So we've got it looking similar to the time that we had before. So previously we had delta t prime equals gamma delta t. And now for the length contraction, we've got delta x prime equals 1 over gamma delta x. As we saw previously, the length dilates or extends, so we see things move slower. But for lengths, they contract. That's why it's called length contraction. So we see that the relativistic length will be shorter than the non-relativistic length. That's basically it for length contraction. Fairly small lecture, but it'll be important because now we've got a way to lengthen and contract time and a way to lengthen and contract lengths. And we've also started using gamma instead of 1 over the square root of 1 minus v squared over c squared. Thank you for listening.